Good morning, everyone.
Good morning.
Morning.
So I'm not sure if y'all are paying attention, but we actually only have 5.5 weeks of classes left. We are almost done. How's the semester treating everyone so far?
Not too great.
Yeah, I agree. Some classes worse than others.
Yeah. Sadly, that kind of seems like it's this theme for everywhere in the world right now for this semester, not just at UVI. And part of the reason why I went to 2 days a week that we're just meeting on Zoom is to try to stay away from Zoom fatigue, since it is a real thing, but we're also playing a double-edged sword with that. So hopefully it's not my course, but I understand. However you feel is how you feel. All right. There's the link again. I see that it is 8 o'clock. So I am going to open up the daily quiz now. So let me share it so we get it for the recording. So what is the vertex of the quadratic function f of x equal -2 times x plus 3 quantity squared minus 2? Write your answer as a point. So you need to fill in the x coordinate and the y coordinate for the vertex. We're missing a lot of people today. All right, I'm just going to give y'all, say until 8:04, which is another minute and a half, especially for some people who might be coming in a little late. Let's see, we've got 17 people here. All right, just saw one person come in, so I'm going to say one more minute until I lock it, or lock answers. Overall, good job so far, y'all. We're just missing 5 responses, so make sure you get your answer in. Wrong answer is much better than no answer. All right. 15 seconds. I'm going to lock answers here in 15 seconds. Ten, 5, 3, 2, 1. I am locking answers now. Please type something in at least. Thank you for at least typing something in, someone. Locking now. Yeah, it looks like we got everyone. Awesome. So strong majority of y'all, probably like 75, 80% got it correct. The answer is -3, -2. So every vertex, every quadratic that is of the form, well, not every quadratic, the quadratic that we start with, the x squared function, nice little vertex at 0, 0. And then I just need to see, okay, from x squared to this, mainly what are my horizontal and vertical shifts? Well, vertical shifts are usually the easier one to spot. It's just what I'm adding or subtracting here at the end. So I can see that this is a shift down by 2. So that means that vertex is 0, 0 is going to go down 2, which means the y-coordinate will become a -2. And then I have to look inside before I square and see how do I modify my x values before I apply this parent function, before I apply the x squared. And remember that you can look at it 2 ways. One, the general form. General vertex form of the quadratic is saying, okay, the x-coordinate is whatever I am subtracting from my x value before I square it, which means since I see a +3, I am subtracting a -3. Or if you remember it from your shifts, since I'm adding a 3, this indicates a, let's see if I can fit it up here, a shift to the left. 3 units. And if I shift this thing to the left 3 units, that means I go from the x-coordinate being 0 to the x-coordinate being -3. Just 2 ways to generate those 2 values. Either way, your final answer is -3, -2, and all but maybe 1 or 2 of you at least said +3 if you didn't get -3, -2, which is a common and a decent mistake to make. So overall, good job, everyone. So, as always, anyone have any questions? And if not, give me a thumbs up so I know we can move on. Please ask questions if you got them. All right. Not hearing any questions and just seeing thumbs up. So we will be moving on for today's stuff. So part of the next couple sections, or the rest of this section and some of the next one, is graphing polynomials. And then finding ways to make graphing and finding roots a little bit easier. So in section 3.2, which is videos that you should have watched before coming today, at least one of them, there's 2 key things that we use to sketch graphs. First one is your end behavior of your polynomial. And what we mean by end behavior is if we have a graph of a polynomial function, let's say it looks like this. So that blue line. We can see that we have roots in the middle because we see that we cross through the x-axis. That's part of it. But then what we're talking about in behavior is what directions are my functions going as I travel to the left or as I travel to the right. So as I travel to the right, on this case, I see that my end behavior is that my function is just going to keep going up and to the right. Okay, So as my x's keep getting larger and larger and larger, my y values are also going to continue getting larger and larger and larger. And over here, I see that as I travel to the left, my y values are going down. A little bit more of an arrow. So the end behavior for this function, there's some mathematics we can write, but our book, and really I don't want to take us through it. We're just going to write the arrows for the directions of which way the polynomial is going. So I would say the end behavior of this is as I travel to the left, it's going down. As I travel to the right, it's going up. There is some interesting stuff happening in between those ends, i.e. those roots. That's not what we're focused on right now. We're just going to be focused on end behavior. And to determine end behavior, you have to use what the book calls the leading coefficient test, i.e. you have to look at the degree and leading coefficient of the polynomial. So if you go back to poll everywhere, you should have a new question, one that you should be able to answer. So I'm going to share screen so we get it for the recording. So we want to use the leading coefficient test to determine the end behavior of the graph of the function f of x is equal to negative 3x to the 8th plus 4x cubed plus x minus 1. And really, anytime we're determining end behavior, we always just have one of these 4 scenarios that you're given for your 4 options. And it's just picking which one is the appropriate one. So I'll give you all about a minute or maybe a minute and a half. I'll just say 2 minutes total. Give you a chance. This is really, it becomes a skill of once you can see the polynomial, you should be able to figure out like that what the end behavior is. First time, it might not be instant, but it's a skill that you want to develop. And remember, these arrows that we see for answer choices are just talking about the tails of the polynomial, the very far ends. Kind of like we saw in that little sketch that I gave. I see a couple more people in here, so let's make sure everyone's got the poll everywhere link. All right. Got most responses in. We are missing just 5 people. Make sure you respond. Just walk away from your computer. I know there's a couple people who do that in this class. Looking for 2 more responses. 2 more responses. We can move on. I'm going to lock answers here in 30 seconds. Actually 15. Let me do 15 since pretty much everyone else is done. All right. A little longer. All right, 5-second warning. 4, 3, 2, 1. Locking answers now. All right, so, hey, we got to 17. I'll take that. Just missing 1 person. So again, over, let's see, 53% of you got it correct. It is that last choice. Both of them are going down. So that leading coefficient test, I'm just going to write leading coef, C-O-E-F-F. That's just shorthand for coefficient. Test really just gives us 4 different scenarios. We have to match, mix, and match. First one is based off of that leading coefficient. The other one is based off of the degree of the polynomial. We can get a nice little box. Move it over some more. So, leading coefficient, the two things we care about, whether or not the leading coefficient is positive or negative. And then the degree, the two things we care about, whether or not it's even or odd. And from this combination of a positive or negative leading coefficient and even odd degree, we get 4 scenarios. If we're positive and even, then both my tails are going up. In this case, you can think of something like the graph of x squared. X squared is an even degree polynomial. Leading coefficient is 1, it is positive, and we know the parabolas just keep going up. However, if I have an even degree and a negative coefficient, they go down. An example would be negative x squared, right? Just reflect that parabola over the x-axis. Now it's facing downward. Both tails are facing down. For our odds, if we have positive leading coefficients, our tails are going to look like the following. As I travel to the left, I go down. As I travel to the right, I go up. You can either think of this as x or x cubed. Both of those functions are functions that we know that fit positive leading coefficient and odd degree polynomial. And then last but not least is if I have odd degree and negative leading coefficient. As I go to the left, I travel upwards. As I go to the right, I travel downwards. So think of the line negative x, that's an example, or negative x cubed. Okay. So when I go look at this function in Polar Everywhere, I say, okay, well, what is the function? And then what is the leading coefficient? And what is the sign of the leading what's the degree and sign of the leading coefficient? Sorry, I was trying to think of too many things in my head at once. So we had 3x to the 8th plus 4x cubed plus x minus 1. All we have to do is focus in on my highest degree term. So leading coefficient is -3, i.e. a negative number. My degree is 8, which is even. So then I go look at my chart. And I see that my chart says my end behavior is that both of my tails need to be pointing down. So that is why it's the last answer. Okay. Questions? If not, give me a thumbs up, please. Questions, questions, questions. I only saw about half of y'all give me a thumbs up. I'm not hearing questions from anyone. So hopefully y'all are still there. Thank you, thank you. All right. So now that we've got that again, whoops, not that problem. Wrong activity. I want to do that one last. We are going to do this problem next. So I've activated a new problem on Poll Everywhere. Should be able to answer it relatively quickly now. I'm not going to share it yet because I want to leave this leading coefficient test up for y'all. But again, same problem, set up with the problem, but this time the function is x to the 11th minus 4x to the 9th plus x squared plus 14. So the function is x to the 11th minus 4x to the 9th plus x squared plus 14. I'll give y'all about another minute and a half from now to select your answer. minus 4x to the 9th. All right. Looks like I'm looking for just, we have 21 people now, so 2 more responses at least. Let's get that poll everywhere up for everyone. Just joins. Make sure that you respond, please. I'm going to lock answers here on this question, though, here in 15 seconds. Five, 3, 2, 1. All right, I've got questions for y'all. So make sure you are paying attention and you are ready. So I have written up the function that we're considering for this question on poll everywhere. Again, it's that x to the 11th minus 4x to the 9th plus x squared plus 14. I want to know from someone, what is the degree of this polynomial? Yeah, it's 11. Because to find the degree of the polynomial, all I need to do is look for the highest exponent. I see the highest exponent here, and that's the term I'm going to focus in on. So the degree is 11, and then 11 is what type of number, even or odd?
Odd.
Yeah, it's an odd number. So that's all that I need to know from the degree. And then the last question is, what is the leading coefficient? All I see is an x to the 11th. What's its leading coefficient?
1.
Yeah, it's 1. If I don't see a number there, it means I'm just multiplying it by 1. So the leading coefficient is 1. And then we said when we're looking at leading coefficient, we just need to figure out whether or not this is positive or negative. Well, 1 is a positive number. So then all I need to do is go look at my chart and see where I have an odd degree, positive leading coefficient, and then that's the end behavior that I'm going to have. Well, positive leading coefficient, odd degree, means that this right here is what my end behavior is going to look like. As I travel to the left, I'm going to be going downwards. As I travel to the right, I'm going to be going upwards. So the correct answer would have been that second one. We go down into the left, and then up into the right. Okay. So leading coefficient, just mainly once you remember this box, you'll always be able to find the end behavior of any polynomial. Okay? So a lot of people got this one mixed up. So I'm expecting questions. So ask questions if you got them. If not, please give me a thumbs up. We got 6 thumbs up. Right now 7, 8. We got 19 people and only 8 people responded. Give me a thumbs up if you are present and are listening to my voice right now. Still missing 5 people. Wow. So then for those of y'all who didn't respond with a thumbs up before, you don't have any questions, make sure you're asking questions. Please, please, please. Now we're going to keep moving on. All right. So that is the first tool we're going to get for being able to sketch polynomial functions. And the second tool deals with roots and their multiplicities. So the first thing we want to do is determine what roots we have and then how often we see those roots appear, which normally means we're going to have to factor a polynomial and then look at that, answer that question. But in this question, I went ahead and gave us a polynomial in a factored form. Remember, multiplicity is just how many times you see that root occur, that factor occur. So in this case, I'm going to give you all the function f of x, which is x minus 1 times x plus 2 to the fourth times x minus 3 squared. So looking at these, I would trust that by now we can figure out what the roots are. So I went ahead and gave them to you in order from smallest to largest. I have a root of -2. It comes from this factor x plus 2. Because if I plug in -2 here, this term will be 0, making my entire function 0. I have the next one is a 1. It comes from this term right here, x minus 1. And then similar with 3, I have my x minus 3 here. The root for this function comes from this term, and it's an x minus 3 quantity squared. So what I want you to do is answer what the multiplicities of these roots are. You're going to make a comma separated list. It just means write a number, comma, number, comma, number. And the first number I want to correspond with the multiplicity of -2. The second number correspond with the multiplicity of 1. And the last number correspond with the multiplicity of 3. And so you need to be typing in 3 numbers, and 3 numbers are the multiplicities. Awesome, already got one answer in. Someone watched the videos. And just similar to the leading coefficient test, this one is you see it. There's not really any work to do it. Mainly because I've already given you the factored form.
So are we supposed to write the roots and then write the comma multiplicity?
No, ma'am, I just want the multiplicities.
Okay.
Thank you for asking, though. Just the multiplicities. But if you write it out, that's fine. You'd want to write it out on your homework, but I know it's much more to type in, so I'm trying to limit how much you'll have to type. And your answer is not what are the roots, it's what is the multiplicity of the roots. What is the multiplicity of the roots? Cool. Let's see, I'm going to give you all one more minute. Just finish typing in your answer. So at 8:30 is when we're going to lock talk and then move on. for the most part, about half y'all have responded. Good responses. All right, I didn't give you all a 10-second warning. I'll give you a 10-second warning now. We'll lock the answers here in 5, 3, 2, 1. Locking answers now. All right, so go ahead and come back to poll everywhere for me. So we need to talk about this. I'm just hoping that it was just more confusing about how to type it in versus you actually identifying multiplicities based on some answers. Okay. So from this function, I went ahead and already gave it to you factored. And when I do that, we can quickly get what the roots are. Right? I went ahead and gave them to you in the problem and gave them to you in order. I have a root of -2, and it comes from this term right here. I plug in x being -2. That term that I just underlined in green will be 0, making the entire function 0. We also have a +1 and a +3 coming from x minus 1, and then the +3 coming from x minus 3. Now, one of the things we're talking about, the thing that we cared about, is the multiplicity of these roots. Let's see. All right, and that is just, again, how many times do I see that root appearing? So I look at -2. What is the factor associated with -2? It was this x plus 2. And how many x plus 2s do I have?
4.
Yeah, I've got 4 of them. I look at that exponent. I have 4 of those x plus 2s, which means I have 4 times where I see this root of -2 appearing, which means that the multiplicity is 4. Multiplicity of this root is 4. What about for 1? Well, similar story. I say, okay, my root is 1. I go look at the factor. I see that its factor is x minus 1. How many x minus 1s do I see there? Well, I just see one of them, which means it has a multiplicity 1. And last but not least, do the same thing for 3. Go look at its factor that's associated with it, which is that x minus 3. And then I say, how many times do I see an x minus 3? Well, I see it 2 times. So then the multiplicity of the root 3 is what?
2.
2. So we have the multiplicities are 4, 1, and 2. So if you're just kind of wondering what you needed to type in to technically be correct, it'd be 4, 1, 2. But really what I care about is if you identify those multiplicities correctly. Okay. So just in identifying multiplicities, take the factor. How many times you see that factor is how many times you see that root. And that's what we mean by how many times that root occurs. So give me a thumbs up if you're seeing it now, especially maybe you just didn't understand what you needed to type in, but you got the right answer. If not, ask questions, please, please, please. All right. So the reason why when we're studying for how to sketch these graphs, the reason why we care about multiplicity is because when we look at a graph and we look at the multiplicity of a root, it tells us what the graph's behavior is going to be like at that root. And so when we're sketching our graphs at those roots in the videos, you would have seen that if you have a multiplicity, I'm just going to shorthand it for mult, talking about multiplicity of our root here. If it had an even multiplicity, this means on your graph, you kind of bounce off the x-axis. Let me write bounce off x-axis. Right, you're going to come touch the x-axis because at that root, it's got to make the function 0. And then you bounce off. You don't change your sign. If you're negative when you're approaching that root, you're going to go back down to being negative. If you're positive when you approach that root, you go back to being positive. That's why in the video he's saying you just don't change the sign. If you had an odd multiplicity, what the graph does is pass through the x-axis. It just goes straight through the x-axis. And this is the behavior, this is why we care about identifying whether or not we have an even multiplicity or an odd multiplicity, because that informs what our graph is going to look like around those roots and allowing us to sketch those polynomials. So, just a quick example here in Zoom, sorry. We'll look at two very simple examples, quadratic functions, which we should feel more comfortable with. So if I wanted to sketch the graph, the graph of this function. Based on the stuff that we learned last week, I know I can just take the x squared function, and this would take it as a horizontal shift to the right. Meaning that if I wanted to draw a nice little rough sketch, it would have a vertex when x is 1, it would still be facing up. And now it would go through, let me rewrite this a little bit, scale a little better. And now I'll have a vertex at 1, 0. I can find the y-intercept really easily. Y-intercept just lets x being 0. And when I do so, I'm going to go through the point 0, 1, which also means I'm going to go through the point 2, 1. I'm going up like this. So this is just a nice sketch. Right? I'm not saying draw the exact graph. I'm just giving a sketch, giving the general behavior, giving maybe a couple points here or there, a couple key points. But take this in the lens of what we've been talking about today. When I'm considering this function, f of x, which is x minus 1 squared, and if I followed it out, would give me x squared minus 2x plus 1. If I look at this and find the leading coefficient and the degree, well, the degree is 2, the leading coefficient is a 1. It comes from that x squared term, which is an even number and a positive leading coefficient, and based on that chart, means that my end behavior, my two tails should be pointing up. Both my tails should be pointing up. And do we see that with our sketch of this graph? Absolutely. As I go to the left, I'm traveling up. As I go to the right, I'm traveling up. So we didn't have it established, but there is this correlation. This is why this stuff works. Then more importantly, with this root, there's only a single root for this function x minus 1. And what is the root? X being equal to what?
1.
Yeah, thank you, Ashley. Next question I ask, and I want you to respond. You're too active. Thank you for being here. and paying attention and responding. I want to hear from other people though. So we get a root is 1. What is the multiplicity of that root?
Two.
Yeah, thank you. Multiplicity is 2. And based off of what we were just talking about, if that root has an even multiplicity, we should see that our graph bounce off the x-axis. It shouldn't change the sign. Is that what we have here? Absolutely. Right? I'm coming down to the x-axis. I'm coming down to where I see my root, and then I bounce off the x-axis. As I'm coming from the left, I was going down, but I was in positive numbers. I bounce off the x-axis, and I stay in positive numbers. Okay, so we had secretly been doing this previously, but just from a different lens. Questions so far? Because I want to do one more quick example talking about that multiplicity, and then I got a problem for y'all to do. But questions? Not, give me a thumbs up.
Before it gets too late, can you go back to the next screen so I can write one more thing down? Sorry.
You're good. Any questions while we're looking at this? All right. So now I'm going to go ahead and move on. Apologize if that's not enough time. So next one I'm going to look at, next function I want us to look at just really quickly is this one, x minus 2 times x plus 2, which if I FOIL it out, becomes x squared minus 4. And if I look at it as x squared minus 4, again, based off the stuff that we covered last week, I know this is just the x squared graph shifted down 4 units. And I can also see what my roots are. So if I quickly just sketch the graph from that to, I'm going to need more. Let's go farther down. Whoops, I didn't mean to erase. 1, 2, 1, 2, 3, 4. Just a quick sketch. I know I have roots at -2 and 2. My vertex is at 0, -4. And my graph will look like this. Again, if I go through that process of leading coefficient and degree, I see that, well, for the x squared minus 4 for this function I'm caring about, my degree is 2. Again, it's still even. My leading coefficient is 1, which is still odd, which means that I should have, my end behavior, my tail should be pointing up. And I look at my roots and their multiplicity. Well, I see that my roots are -2 and 2. The multiplicities are both 1, because I only see the factor x minus 2 and x plus 2 appearing once. So that means that they, at each of these 2 points, pass through because of that multiplicity. And that's what we saw. That's what we see right here. At the roots, my graph passes through the x-axis. It changes sign. Both cases, they go from negative to positive numbers. Okay? So this is the correlation between what we've already established and this new stuff, leading coefficient test and roots. Okay? I see the time. Any quick questions on this so far? I got one example that I want y'all to do on your own before. Not, give me a thumbs up. Thank you, Leah, for picking up on that, and Chris. There we go. Now I'm seeing some thumbs up come through. All right, so go to poll everywhere. And this is kind of the combination of all of the stuff that we just talked about today. This time I'm giving you a cubic function. So it is the function x cubed minus x squared minus x plus 1. So the function is f of x is x cubed minus x squared plus x, or minus x, sorry, plus 1. And what I want you to do is, using leading coefficient test and roots and their multiplicities, just get a rough sketch of what this graph looks like. And then from your sketch, try to select which of the 4 options you have in poll everywhere best matches your response. Just so I have some more time to talk about it and we don't go too far over, hopefully won't go over 8:50, but I'm going to give you all just a minute and a half. I know that's not a ton of time to do it, but just get as far as you can, get your best guess. Use your sketch, use all of your information that we've gathered today to give you best guess at what this graph will look like. So not only end behavior, but finding the roots. Oh, and here's your hint to find the roots. Factor by grouping, right? That was our way to factor cubic polynomials. Factor by grouping, get your roots and the multiplicities. All right. I'm not going to lock answers, but I'm going to go ahead and start talking about this. Like I said, I just want to make sure we're out of here as close to 8:50 as possible. So if you're still working on it, that's fine, but go ahead and bring up your Zoom screen so you can see the whiteboard that I'm sharing. Okay, so when I have it in this form, x cubed minus x squared minus x plus 1, I can already spot from this form relatively easily what's leading coefficient and what's the degree. When I look across, I find the highest exponent that I see, which is a 3. So I know my degree is 3, which means this is an odd number. And my leading coefficient for the x cubed term, well, I don't see it being multiplied by anything, which means I'm actually multiplying by 1, which is a positive number. And if I have an odd degree and a positive number, that means my end behavior should look like this. Traveling down and to the left after I've dealt with all of my roots, and then traveling up and to the right after I've dealt with all of my roots. So I know those are what my tails are going to look like. After that, I have to factor. And the hint that I gave you all was factor by grouping. If I look at these first 2 terms, they have an x squared in common. So I can factor out an x squared, leaving me with x minus 1. And then once I see that the factor that's left over is an x minus 1, I kind of have it here, except I have a negative x plus 1. So what I'll do is I'll just factor out a minus sign, and that will leave me with an x minus 1. And I know this is correct because if I distributed that minus sign back through, that'll give me that negative x, and that'll give me that positive 1. That means both of them have a common factor of x minus 1. I can factor out, I mean, with x squared minus 1 times an x minus 1. I look at that x squared minus 1. I can factor that into an x plus 1 times an x minus 1. I still have this nice little multiplication of x minus 1. So all I've done here is factor x squared minus 1, which leaves me with an x plus 1 times x minus 1 quantity squared. So now that I have the factor form, again, I can now find my roots and their multiplicities. Well, my two roots here are -1 and +1. The root -1 corresponds with this term. The root +1 corresponds with this factor. And see how many times I see those factors appearing? Well, I see x plus 1 appear once. I see x minus 1 appear twice. So this tells me that whenever I'm approaching the root at x being -1, my graph should pass through. And at +1, because as an even multiplicity, it should bounce. So if I sketch my graph real quick, just using those pieces of information, I know I have to go through the 2 points, -1, 0, and 1, 0. After my last root, I know I need to be going up and to the right, but at that root, at +1, I bounce, which means my function would be going up. I could plug in x being 0. I'll see that my y-intercept would end up being a 1. I got to come back down to this root because I know I got to hit the x-axis there, but at -1, it says that I pass through the x-axis because it has an odd multiplicity. And then I see after that, I have to make sure my end behavior matches, which it does. So I pass through at -1, I come down, I touch the x-axis at +1, bounce off and keep going up, which means that if I'm looking at all of those answers, it'd be the very, very last one. Okay. So I'm 851. If you felt comfortable with this, you understand, you followed along, you're more than welcome to give me a thumbs up and then head out. If not, you can stick around for a moment if you got time and ask questions. Because remember here, when this black graph in the bottom right that I'm drawing is just a sketch. It's not exact, it's just to inform. Right? The specific graph is what you're selecting. All we were doing was trying to sketch it. So questions?
The last graph.
What was that? Sorry?
The answer was the last graph, right?
The very last one. Any other questions? So what do you mean by go over the graph, Mona Lisa? Like how we got it, just overall? Or like the roots, the bounce part. Okay, cool, cool, cool. So again, comes back to this. If our roots have an even multiplicity, that means it's going to bounce off the x-axis. If it has an odd multiplicity, it goes through. So when we found our roots, so let me try to eliminate some of the color and clutter. So when we factored our function down, we saw that we had two roots, -1 and +1. They came from our two factors, x plus 1 and x minus 1. And all I need to do is say, okay, for the roots, what's its multiplicity? Well, -1 had a multiplicity 1, +1 had a multiplicity 2. So if it's an odd multiplicity, it goes through the graph. If it's an even multiplicity, it bounces off. So when I draw my sketch, I know I have to at least hit the x-axis when x is -1 and y is +1. And that's what we see at both of those points. But because we had an even multiplicity at -1, we needed to pass through. That's what we see. We're going from, if we're traveling from left around the x-axis, we go from negative numbers to positive numbers. We go through the x-axis. However, when x is 1, you can see that I'm bouncing off. I'm coming down to the x-axis because I know I got to hit that root. I went up some, now I'm going to have to come back down to the x-axis. But because of that even multiplicity, I bounce off the x-axis. Think of it just like a bouncy ball. You throw it down at it, and it's just going to come right back up. And so we see it goes right back up, and that's also necessary because it needed to match my end behavior, which says after all my roots are dealt with, I just need to be going up and to the right. And so even multiplicity means we bounce, and that's the type of behavior that we see. We're coming from positive numbers, we come down, touch the x-axis, we go back up to positive numbers. Just by plugging in 0 into my function. Good question. So that's how we always find y-intercepts, is just by plugging in 0, and that'll tell us what the y value is. So where we go through on the y-axis. So 0 cubed plus 0 squared, or not plus, minus 0 squared minus 0 plus 1 gives me a 1. So that's how I get that 0.01. When x is 0, my y value is 1. Awesome. No, thank you for asking questions. I want to clarify things. So, questions from anyone else, or any more questions, Mona Lisa?
I think I got it now.
Perfect. So awesome. I'm not hearing anything else from the other two, so I'm going to go ahead and end the meeting. But I will see y'all tomorrow, nice, bright and early at 8 a.m. Have a good rest of the day.
Okay, you too.